Thank you for that intro. So yeah, this talk is about the Lustre timeout hierarchy. I'll have a little introduction, kind of introduce the motivation for this topic. These are the wrong slides. These are the wrong slides.
You go with the PowerPoint? Oh, okay. Sorry. No, this one. Those?
Yep. Okay. No, that's my fault. You've been doing a great job, Stefan. Right, okay, so talk about sort of our motivation for this topic, what our goal is in tuning the timeout hierarchy before diving into the timeouts at some of the software layers, talking about things to think about when you're tweaking those values, and then discuss some new changes in this area and some future work. So the motivation for this talk actually stems from work that started way back in 2014. At that time, Lustre 2.7 was under development, and Cray and the cluster store team that was at Seagate were working on addressing problems with resiliency in the face of message loss. I wrote, we set a goal to be able to ride through some message loss without client eviction, but what really happened was that we had a salesperson write into a contract that we had to be able to survive a router crash without client eviction. And there's nothing that motivates problem solving like contractual obligation. So our solution to that involves some code changes to enable resends of RPCs that revoke client locks, and then proper tuning of the timeout hierarchy to ensure that those resends could occur in a timely manner. So I wrote a paper on this topic for the Cray user group in 2015. A copy of that is on the lustre.org wiki. We also, at that time, created an internal document that was a deep dive into the timeouts and how they kind of all interact with each other. That had not previously been shared before. But the reason that this topic is still relevant today is that in modern Lustre, the timeouts at the different layers are still not tied into each other, right? And the default settings are not always correct for all configurations or to leverage all of the available features. So I hope to, kind of provide an overview of these different parameters, and so to kind of give people confidence if they want to go in and change these things to try and optimize. And then lastly, so a copy of that internal deep dive document I mentioned is now also on the lustre.org wiki. So just starting with the basics here, syscalls, read write stat, filter down through the various Linux and Lustre software layers where they're implemented through a series of remote procedure calls, or RPCs. These RPCs are prepared at the portal RPC layer, and once they're prepared, they're passed down to LNet, which is network type agnostic, abstracts away underlying network from the upper layers of Lustre, and LNet uses the Lustre network driver layer to interface with the drivers for specific network types like HP Slingshot, InfiniBand sockets, EFA. And so these, three layers that I've highlighted here are where we'll kind of focus our discussion. So before we dive into the timeouts at those layers, I want to talk a little bit more about the goal in tuning the hierarchy. Again, the primary goal is to avoid client evictions due to failed blocking callback requests. So At a high level, clients will request a lock for some file resources in order to perform various operations. And when a conflicting lock request comes in, the server issues a what's called a blocking callback to revoke the granted lock. And when the blocking callback is issued, the server starts a timer we call the lock waiting timeout. And then the client has to complete any outstanding operations that it has where it needs that lock before it sends a cancel to the server, releasing the lock, and that allows the server to grant that lock to the new client. If that cancel isn't received when the lock waiting timeout expires, then the client is evicted, and that allows the lock to be granted to the second client. Evictions are nasty because they tend to result in EIO-like errors that applications generally don't handle, and so you typically get application failures when clients are evicted. So we don't want to evict clients unnecessarily. So the idea is that we want to tune timeouts so that the lock waiting timeout provides sufficient time for a client to complete its work, even if there is some transient RPC failure. So for example, if the client gets a network error when it's trying to send that final cancel RPC, we want to ensure that the lock waiting timeout is large enough that the client can get reconnected to the server and resend that cancel RPC without getting evicted. Okay, so let's talk about the timeouts at these different software layers. We'll start at the bottom with LND. The main one here is just the LND timeout, which is pretty straightforward. It's the total amount of time that the Lustre network driver will take to complete a network transaction, whether that's a successful one or not. It needs to account for different characteristics of different networks, right? So it's typically not appropriate to have just one LND timeout that works for all network types. So for example, O2IP LND and SOC LND are both connection-oriented protocols, so they need to establish and maintain connections between peers before they can send other traffic. KFI LND is connectionless, right? So that's overhead that it doesn't have. Another example is O2IP and KFI both have receiver not ready retries, which is kind of like a handled a little bit further down in the network stack, where if there isn't a buffer posted for a message that's incoming, then it'll just automatically retry until it completes or fails. And so, if you have a network that supports that, your LND timeout needs to account for the time for the R&R retries. Yeah, this is typically derived from these LNet transaction timeout and LNet retry count parameters, which I'll talk about in the next slide, though they can also be set explicitly with kernel module parameters, or I think now you can set them in the YAML-like config. So at the LNet level, the picture on the right really just, kind of tells the whole story, right? So you have, LNet has the ability to resend messages before, or attempt to resend messages before it bubbles up errors to upper layers. And so the LNet transaction timeout needs to account for how many times it could resend a message, right? So that's just some multiple of the LND timeout. And the transaction timeout is also used for some other multi-rail features, response tracking, and peer discovery. The defaults for these have changed between 2.15 and 2.16, basically just growing the LND timeout, which has implications for tuning the portal RPC timeouts. So at portal RPC level, we use the Lustre adaptive timeouts feature, which just tries to factor in how much time the server, it's adaptive, right? It changes over time. It tries to measure how much time the server is spending to process RPCs, how much time is spent on the network. So it adapts to both load on the network and load on individual servers, or even individual services running on a single server. And both of these components, the RPC processing time and the network latency time, are bounded by ATMIN and ATMAX parameters. So simply, the RPC timeout is just the sum of those two components. And since they're both bounded on the low end by ATMIN, we know that the RPC timeouts are going to be greater than or equal to 2 times the ATMIN. There's more details and things. Adaptive timeouts is a little more complex than what I've described here. There's a talk in LUG 2023 by Rick and James that discuss more of that. So if you're interested in kind of more about adaptive timeouts, I'd suggest you go look at that. What's relevant for this discussion is that the default ATMIN in 2.16 is 5 seconds, but the default transaction timeouts and L&D timeouts are much higher. And so, that's kind of what I mean by, with the default values, you're not leveraging, you can't leverage the LNet resend feature, right? Because your RPC is going to time out before LNet or even the L&D has finished sending the first one. So if you want to leverage LNet resends, then you need to tweak the timeout hierarchy to provide sufficient time for that. So on that topic, if we're looking, how does the RPC timeout get assigned? We can look at the code. It's pretty straightforward. We assign a deadline to our portal RPC request, so that's just some offset from the time that portal RPC hands the message off to LNet. That offset is what I described before, right? It's the sum of the estimate based on the average RPC processing time and estimate based on the average network latency. And so if you want to leverage LNet resends, we can come up with a relationship, right? So your RPC timeout, we know from the previous slide, is greater than or equal to 2 times ATMIN. And to leverage LNet resends, it needs to be higher than the LNet transaction timeout. So we know that ATMIN has to be greater than the transaction timeout over 2. Special consideration for router configurations, right? By definition, you have routers bridging disparate network types that may have different transaction timeouts or L&D timeouts, right? But the LNet transaction timeout is global. There's only one. So on a router, the question is, which value do I use? And so the guidance here, right, is you just don't want to end up in a situation where you're sort of defining an L&D timeout derived from the transaction and retry count that is lower than what your L&D requires, right? So KFI needs a rather large L&D timeout, IBLND a smaller one, right? So we, on a router bridging KFI and IB networks, we use the values that give us the KFI timeout, basically. One other thing about router configurations, there's a router checker feature which just pings routers at a fixed interval to determine their aliveness. And it has its own parameters that relate to the transaction timeout. Since it uses LNet peer discovery, the LNet transaction timeout is what determines whether or not a discovery ping succeeds or not. For some reason, there's a separate router ping timeout variable, but it really ought to just use, or parameter, but it really just ought to use the transaction timeout. And then there's a parameter to define the interval at which these pings happen. So you just need to make sure that that's larger than your transaction timeout. Okay, so more on how we define ATMIN, right? We know from previous discussion that it needs to be larger than LTT over 2, the transaction timeout over 2, if you want to leverage LNet resends. again, in a situation like this, in a router configuration, you might have different transaction timeouts in your clients and servers, but there's only one ATMN. So the guidance is to use the largest one. You want to account for some amount of processing time on your router. If you have a router config, we just call it 5 seconds. And we throw in 5 seconds for RPC processing time. So you get this simple little formula that takes in the transaction timeout and spits out what your ATMN should be. And so with the default values in 216, you get 80 seconds, which seems like a lot. And I'll talk more about that. One more parameter here, the bulk timeout server side only. So in a bulk IO, bulk read or bulk write operation, you have a bulk request client sends to the server that's covered by the normal RPC timeout mechanisms, but then the bulk transfer portion where you're actually moving the data, there's a separate bulk timeout parameter. But again, if there's a network failure, LNet could resend that using its LNet resend feature. And so if you want to leverage that, you just want to make sure your bulk timeout is larger than your LNet transaction timeout. So back to our tuning goal, just to kind of tie in how those timeouts we discussed factor into helping us avoid client eviction. We don't want to evict clients unnecessarily, so we want to make sure that the LWT provides sufficient time for the client to complete its work, right? So this is kind of a worst case, right, where you've got a interface failure on a server, so the client actually needs to, its options for having successful network traffic have been halved. So the first thing that happens, right, is you have an RPC timeout, and we know that that's at least 2 ATMN. After the RPC timeout, the client needs to send a connect RPC to get reconnected to that target. And for this, there is a separate, it's called initial connect timeout, which defaults to 5 seconds. And the idea here, right, is if you really have a transient network failure, then your reconnect ought to be successful and quick. And then we need to factor in the network latency, so that's an additional ATMN. And then finally resend that RPC that originally hit the timeout, which is another 2 ATMN, right? So in the code, you can go look at how this lock waiting timeout gets calculated, and if you kind of translate the various variable names, you come up with this relationship. So it's 5 ATMN plus this initial connect timeout. The last parameter that I'll mention is this LDLM and QMIN parameter. And this is really just for rare cases where the LWT may not actually cover your worst case. This was particularly relevant on the Aries network because the whole network could quiesce for minutes, which wasn't really reflective of your normal network latency, network characteristics, right? So you didn't necessarily want to bump up ATMN to minutes, but you want to make sure that clients, this lock waiting timeout could survive a quiesce, right? So as part of that CUG paper and that, our deep dive, we came up with this formula for LDLM and QMIN. So, yeah. So 80 seconds is a lot. If you factor, if you plug that into the LWT, right, 5 ATMN plus 5 seconds, that's, over 400 seconds. And keep in mind, right, the lock waiting timeout is how long a client could be blocked, waiting for some client to release its lock, right? And so that definitely you know, a user could notice that, you know, like my Alice is hanging for 5 minutes. So, you know, there are some things you can do, right? So you can tune down the number of retries, right? Or, you know, disable them altogether. And that allows you to lower AT-min and the lock waiting timeout accordingly. At HPE, we typically use 10-second LND timeouts for InfiniBand and sockets, or sock LND. And so with that, we have a transaction timeout of 31, so you can still have some retries and a pretty reasonable 18-second AT-min. That's maybe particularly relevant for like a router configuration, right? Because you typically have many fewer routers talking to your servers than you do clients, you know, behind that. Okay, so, you know, we've been a few people talking about, you know, the desire to make the out-of-the-box experience better and, you know, different facets of Lustre. I think, like, you know, configuration is one where it'd be great if it just, you know, worked, you didn't have to worry about it. So we've been kind of plugging away at towards that goal. So, you know, the LNet transaction timeout is global. There's just one, but particularly on, for example, routers, that's not really appropriate because you have different network types and different characteristics. So we came up with this idea to just kind of dynamically figure out what the transaction timeout should be based on whatever network interface we select for a send. So rather than derive the LND timeout from the transaction timeout and retry count, we do it the other way around, where we derive the transaction timeout from the LND timeout. So that allows us to set static LND timeouts for each LND that should work for most cases. And then, you know, the only thing you need to worry about is whether or not you want to use the LNet, you know, if you want to define an LNet retry count. And then LNet figures out the appropriate transaction timeout based on whatever network it's sending on. And that's landed for 217. Some other future work that we're looking at, so LU 18878, there's another timer that I didn't talk about, the ping eviction timer. So if you have idle pings enabled, your clients that aren't otherwise doing I/O need to ping every target in the file system at some regular interval. If they don't, then you get that message on the server, you know, I haven't heard from client XYZ and I'm evicting it. That usually works, but there, you know, we in testing have run into situations where we'd see a lot of kind of unnecessary client evictions if the network got loaded, and yeah, maybe it's not a big deal because they're idle anyway, but we thought we should extend that lock waiting timeout logic to the ping eviction timer so that, you know, it can factor in the server load and network latency. The other thing is, you know, the lock waiting timer, the logic assumes that that first reconnect is going to succeed. That may not always be the case. You know, we could extend it to account for additional reconnects, but you know, with AT-min 80, right, we're already up over 400 seconds. Do we really want to push it to 10 minutes or whatever? Probably not. But maybe there's some things that we can do. So like one idea was maybe Portal RPC could tell LNet when it's sending a connect RPC, and LNet could remember, okay, well, I'm sending it to, like in this picture, you know, I'm sending it to B at O2IB. And then the next time, that fails, so the next time Portal RPC tells LNet, hey, I'm sending another connect RPC, LNet can say, well, I sent the last one to B, so I should send this one to C, because apparently it didn't work, right? So maybe we can build in some smarts to ensure that each interfaces get, kind of an even distribution of these connect RPCs. So the main, another idea is like a big component of the AT-min in that lock wait timeout is actually just the network latency. But the AT-min consists of both network and RPC processing time. So if we actually split those, then we could bring down the lock waiting time a little bit by getting rid of the redundant RPC processing time. Other ideas, we could derive the LNet retry count from the RPC timeout. So Portal RPC could tell us what an RPC timeout, could tell LNet what RPC timeout is. LNet looks up the LND timeout like I described previously, and then if the RPC timeout is some multiple of the LND timeout, then that's how many times LNet can try to resend it before the RPC deadline expires. LNet retry count is currently global, but again, sometimes it's appropriate to have retries on certain networks but not others, so maybe that should really be a per LND thing. And I think what would probably be best, or most useful, right, is if we could either derive all of the LNet and LND timeouts from the RPC timeout, or the other way around, right? So we get to that point, then you've got, maybe there's one parameter that you set, or maybe you just take the defaults, right? You don't have to worry about anything. So those are kind of the things that we're kicking around and experimenting with. I did include in here some sample configurations. One of the people that reviewed this slide said, like, you can't tell them that the defaults don't work and then not provide working defaults. But so anyway, so these are the ones that we typically use at HPE to set up systems. Like I said, we typically use a 10-second LND timeout for IB and KSOC, and so you can see the corresponding LNet parameters. There's some examples for router configurations and examples for calculating AT-min for different configurations. Thanks.
Question for Chris.
So your timeouts that you use in Cluster Store with Slingshot, their coexistence with other file system mounts that use a different type of LNet, like InfiniBand, if one file system versus the other has different timeouts, obviously that behavior is a problem. Is there like a path to solution there?
Yeah, I mean, so the thing to keep in mind, right, is you want to avoid situations where you're aborting network transactions that will probably complete successfully, right? So like, like I showed before, like the KFI LND timeout is 125 seconds, which is a lot. The IB LND timeout in 216 default is 50 seconds, right? You don't want to use a 50-second LND timeout with KFI because there's a fair amount of situations where you end up aborting transactions that are going to complete successfully, right? So you've only got one global AT-min, which kind of handcuffs you a little bit, right? Because you've got to set that so that you provide all of your L&D sufficient time. Maybe if we had, I don't know, some way to do multiple RPC minimum or adaptive timeout minimums.
So there is actually per device AT, min, max, everything in 216. So we can actually set them separately. It's just that nobody knows, to do that yet. But,
Apparently.
There you go.
So that's per target?
Per target, yeah. So every OSC, MDC device has an AT min setting. Right.
Sweet.
But it's brand new and not really in any of the maintenance branches yet.
It's amazing. So I can give an updated version of this talk next year.
Yep. Yeah. Yeah.
Perfect.
Well, no, and like all of the stuff to do automated, like you were saying, people don't want to know about this, right?
Right.
So, I mean, the one question I would have is with the LNet level read sends, is there some way to make those resends reuse the same receive buffer so that you can resend the request, but either the original reply or the resent reply could come into the same receive buffer so that you're not actually like killing the first request, you're just sending it again.
That's how it works. That's how it works today.
Okay.
Yeah, the LNet resends portal RPC. I mean, assuming the portal RPC timeout hasn't expired, it's still just waiting for, either the. Oh.
I thought it was the opposite, but I could be wrong. We can talk.
Well, no, I'm thinking about whether or not there may be different cases depending on whether or not it gets the request out, callback, and it's waiting for the reply versus not.
Okay, I have a question over here. In this picture and in this report, we look on interaction of individual server, individual gateway, and individual compute. So, and we ping multiple times from different compute nodes and gateways, so everything is redundant. And if some gateway is dead, someone else knows it. So a while ago, it was a project to do LNet or Lustre Health, where all that knowledge about failed component was integrated and feedback to Lustre. So is there some project or thinking about doing LNet Health?
I mean, yeah, I'm not sure. I mean, so if you've got, like in this case, when the interface fails, LNet Health should know about it, right? And so it ought to redirect traffic appropriately. If you've got a failed router, or, so in some sense, Lustre itself doesn't need to know about it, right?
Yeah, so we discuss individual actors. But if you think about system, then 10,000 compute nodes send ping to gateway to figure out that it's dead. But somehow that knowledge can be propagated and other gateways know that it's dead, or servers know that it's dead. Don't try that, don't go and...
Right. So some more like proactive sharing of information. If I learn about, this failure in the network before you do, can I tell you rather than let you figure it out on your own?
Project Eric Barton.
Yeah, so that was like the gossip protocol, right?
Yeah, yes, exactly.
Yeah, there's no plans to integrate that in LNet. It could be a good idea, it could be worthwhile.
I had a question about the some of your future work. So pretty much deriving timeouts kind of bottom up. So from like the L&D layer timeouts, deriving like the portal RPC timeouts and such. I know there exists like the global like OBD timeout that kind of does the opposite, where it's the top down. Do you ever see that going away, or being deprecated in favor of?
Sure. I mean, so I mentioned this 18878. So the ping eviction timer, I think, is before this patch was derived from OBD timeout. OBD timeout was something that was used before adaptive timeouts were implemented. And so if you can still, like if you look at the code, you can go turn off adaptive timeouts and then it will use OBD timeout to derive everything. Yeah, I mean, I'm all for getting rid of it, right? If we don't need it anymore. I don't know what else uses it.
Do you think it's like completely deprecated already, or?
No, not completely. Or I wouldn't think so. So like, for example, I know that it's used, or it was used in the ping eviction timer. It's probably still used to determine the ping intervals for the idle pings. It would not surprise me if it's used for other sort of default values. But yeah, so I don't think it's ready to be deprecated right away, but it probably wouldn't be difficult to do it. But I don't know, maybe there's use cases for it that I'm not aware of.
Makes sense.
Okay. I think we need to do the break now. Thank you, Chris. Thank you again.
Thank you all.
Learn a lot.